This is the second lesson from A-level physics. And remember, I'm just using a board and a pen and my voice, and no fancy animations, nothing special, nothing clever, just that. Today's topic is stable and unstable nuclei. So, stable and unstable. And remember, the reason why I am talking and writing at the same time is because it forces me to go slower, which gives you time to absorb what I'm saying, gives you time to make your own notes, write your questions in the chat, or even give answers in the chat if other people have questions. So let's talk about stable and unstable nuclei. And you'll learn about this in GCSE physics. There are 3 different types of radioactive decay. That's what we call it. 3 different types of radioactive decay. Alpha decay, beta decay, and gamma. And of course, Americans pronounce the beta as beta. We don't have to like it, but they do. We're going to pronounce it beta. So let's talk about each of these radiations. So alpha, written like that. Well, an alpha particle has a mass number of 4 and a proton number of 2. So it is equivalent to the nucleus of a helium atom. Absolutely equivalent to that. The only difference is that it comes from the nucleus of an unstable atom. Now, these are all emitted from a particular isotope with the same energy. From particular isotope with same kinetic energy. Probably shouldn't have done a capital E there, but never mind. They're all emitted with the same kinetic energy. So we've got some nucleus here, just like that, and it's unstable, so it goes ahead and emits a part of itself, a little alpha particle, making itself more stable. That alpha particle carries away some of the energy, the kinetic energy, causing the nucleus that has decayed to drop in energy to become more stable. That's what happens. And so we could write down this process like this. We could say that element X, which starts with Z and A like this, is going to decay into element Y and an alpha particle, which we know is 2 and 4. And I'm going to have to be careful here to make sure my 2s and my Zs look very obviously different. Some people put a line through the middle of their Z to make them even more obviously different. I don't tend to do that, but because there's a risk of ambiguity here, perhaps today I will. And so we need to make these numbers balance. If I have A subtract 4 and I add 4 to it, then that makes A. You can see that. Let's just get my highlighter pen out. A is equal to A minus 4 plus 4. That checks out. That follows. But let's leave that highlighted. And then if we look on the proton number, that's going to have to be Z subtract 2. Because if I have, choose my highlighter pen, perhaps a different color, let's go with the green, Z is equal to Z minus 2 plus 2. It follows. It works. It really does. So let's go into here and write down A. Oh, we can't even see that yellow. Let's write down in an orange color so it's a little bit easier to see. What's going on at the top is A is equal to A minus 4 plus 4. And what's going on at the bottom is Z is equal to Z minus 2 plus 2. So it works. Everything works. Put some brackets around this just so we know it's not that important. So moving on to the second type of radioactive decay, what we call beta decay. Or if you're American, beta decay. Yuck. Beta decay. Okay, so with beta decay, a beta particle, we would write -1 and 0. We could even, if we wanted to, put 2 plus on the top of that, 2 plus on the top of that for alpha, and we could put minus on the top of that to indicate it's negatively charged, but actually we wouldn't really need to bother with that during our physics A-level. Not actually interested in the charge that much. In terms of chemical reactions, you might be using that charge symbol in the top right-hand corner a lot. In nuclear physics, no, not really. That is equivalent to an electron. It is an electron. Now, obviously, an electron doesn't contain -1 protons, but it makes the numbers work, so we stick with it. Now, these have a range of kinetic energies up to a maximum. And that's when they're emitted from a maximum, that's close, that's when they are emitted from a particular nucleus, a particular isotope. So what's happening here? Well, let's do a quick sketch. We've got our unstable nucleus here, and it's going to decay, and it's going to emit not 1, but 2 particles. Now, this process is a little bit more involved than I'm showing you, and we will get on to how much more involved it is a bit later. But it does actually emit 2 particles. And one of them is called an electron antineutrino. Electron antineutrino. It has a long name, whereas this beta particle is just an electron. And I suppose I should probably label this as a alpha particle. No, it's already got the symbol, I won't bother. So what's going on here in terms of chemical symbols, in terms of the reaction itself? Well, let's say we've got X with Z protons and A nucleons. That's going to decay into Y plus a beta particle, which we're labeling like this, but also an electron antineutrino. The bar over the top indicates it's an antimatter particle, but we'll do that in a later lesson. Don't worry, be patient. And we're not going to bother writing 0 and 0. We don't really bother with that. They are there, but we don't need to bother with that. They're not really going to factor into our calculation. So what happens to the nucleon number to make this work, to make this balance? Well, nothing. Nothing changes at all. A is, let's use yellow, keep consistent. A is A plus 0, and of course plus 0 as well, but I'm not going to bother with that. But what goes on with the Z, with the number of protons? Well, that has to go up by 1 to make this balance, as you can see here. So if I get my highlighter pen out, highlight the important bits, Z is Z plus 1 plus -1, and then plus 0, which I'm not going to bother with. So let's write this all out. The first one, what's going on with the A number is nice and easy. A is indeed equal to A plus 0. No one disagrees with that. What's going on with Z is interesting, because we have Z is equal to Z plus 1 plus -1. And that does check out as well. Now, the anti-electron neutrino carries some of that kinetic energy away. So the beta particle and the electron antineutrino share the energy that's released in this decay, which is why there is a range of energies for the beta particle. In fact, it was the range of energies that was first noticed and led to the electron antineutrino being proposed the range of energy for beta particles led to the electron neutrino, or the electron antineutrino, being proposed as a way of answering this conundrum of why did the beta particles have a range of kinetic energies. So let's just read this back to make sure I didn't write something stupid. Beta and electron antineutrino share energy released. That's why there is a range of, that's why there's a range of energy for beta particles. Yeah. The last one is your gamma, and gamma is electromagnetic radiation. The symbol is just gamma. I'm not going to write 0 and 0. I could do. I'm not going to bother. It's just gamma. It's just electromagnetic radiation. That's what it is. And it's emitted from unstable nuclei when they become more stable. So it doesn't actually change the composition of a nucleus. If I have that, it doesn't stop being what it is just because it emits a little bit of electromagnetic radiation. Let's do this like a wavy shape. Just like that. That comes out, but the nucleus doesn't change. Nucleus structure, let's not say structure, let's say composition, unchanged. But there is a change to the energy. So we might have something like X with Z and A, which is in what we would call a metastable state. The particles in the nucleus are in excited energy levels. It's just a higher energy. It's an excited nucleus, which might decay into the same element, but it's no longer metastable, so we don't use that little m, and some gamma radiation. Metastable just means it's not really stable, but it's kind of stable over a long enough time that we can measure it. It's like half stable, kind of stable. Yeah, heart's not in it. So that's what's going on with alpha, beta, and gamma. So why is another question. Why does this happen? And the answer I'm going to give you, I'm just going to talk about alpha decay at the moment, is it's due to the strong nuclear force, or the strong interaction, as we're going to call it later, but let's just stick with strong nuclear force. Now, you know about fundamental forces like gravity, gravitational force, and electrostatic force. You've heard about these. You probably know that a push force or a pull force, they are actually just electromagnetic forces. Actually, they're electrostatic forces. And you know that friction is just another example, as is air resistance. They're all just examples of electrons pushing against electrons with the electrostatic repulsion because they happen to be the same charge. Fine, that's very interesting. But the nucleus contains two types of particles. It contains protons, it contains neutrons, and that's it. And the protons repel each other. The neutrons, they don't have any electric charge, so they're not involved in this. Let's just go back to the previous lesson. We were looking at the structure of the nucleus then. So, if I drew a graph, let's draw a graph of the force, let's do the best graph I can, just like this, of the force versus position. This is x, the position of one proton relative to another, and this is the force between them. So this is the force between protons on this axis, and this is distance between those same protons. And let's say that this part of the graph at the top is showing repulsion. Positive forces are repulsive forces. And this part down here is showing attraction. Negative forces are attractive forces. Well, the electrostatic force does something like that. Let's do a better job. The electrostatic force does something, do a better job. The electrostatic force does something like that. That'll do. That's the electrostatic force. Probably don't need a hyphen in it. electrostatic force. It's always repulsive. And if that was the only force acting in the nucleus, then the nucleus would blast apart because the protons are pushing against each other. The gravitational force between those protons is absolutely minuscule, so we're going to ignore that. So there must be another force acting, and this other force that's acting is a very interesting one. Pretty much nothing happens for absolutely ages. Then it becomes very attractive, and then it becomes repulsive. And this is the strong nuclear force. Now, the resultant force is what you get when you add these two together. You notice it's repulsive, 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 repulsive. That's just red plus green line. And about here, it goes to being like this, and then it will shoot up like that. There's a very interesting thing that's going on. And there are 2 points where it crosses the x-axis, where the resultant force is 0. This one is an unstable equilibrium. We'll have to talk about equilibria later in the course. But basically, if the protons are that far apart, nudge them slightly further apart and the force becomes repulsive and they blast apart. Nudge them slightly closer together and the force becomes attractive and they come together. So that's an equilibrium, but it's unstable. This is a stable equilibrium. If you nudge them closer together, they push apart. You nudge them further apart, they come back together. So that is where the protons sit. That's the distance between them. And you have to know some numbers. That is about 0.5 femtometers, where that happens, and the range is about 3 to 5 femtometers. Femtometers equals 10 to the negative 15 meters. Absolutely tiny, tiny, tiny range. Now, if the nucleus is too big, then this force can't extend from one side of the nucleus to the other. So we need more neutrons to add more of this force to overcome that electrostatic repulsion between the protons. And if the nucleus gets too big, it's actually more energetically favorable just to eject part of it. And that's what alpha decay is. Why is it an alpha particle? Because alpha is very, very stable in itself. Well, we'll stop there. Hopefully you found that useful.